Thank you. Well, I will start by, I wanted to do some introduction as well, and I have an ad for my company. So this is the last game that we made, Gatling Gears, and you can still buy it because on Steam right now there's a sale. So if you want to have a look, see, ad done. And the first question that I'm gonna answer is why debugging? Why not just simply not make bug? Well, there's a lot of talks about that actually, about how to work so that you don't have bugs, so that you think about your coworkers when you work, so that you think what they are going to do, and so there are lots of talks about minimizing the amount of bugs that you can create in a team. But let's be fair, that's not enough, and you will always have some bugs to fix, and they can be pretty tough. So since there's not so much available on the topic, well, I decided to talk a little bit about this. And as I said, you cannot avoid bugs because they mostly come from interaction between modules. If you have worked only on small projects before, where you know all of the code, that's quite easy to make something bug-free. You know, you try it a bit, and after a while, it's very stable. But when it comes to big code base, you have different modules that need to communicate. So you also have different teams that need to communicate, and it's usually where it breaks. You make assumptions about the code, and usually the assumptions are wrong, and then you get just a bug. And so there's a way to minimize it, but there's no way to avoid creating bugs. Let's take an example. So this is a very simple code that already has a bug here. And if you don't see it, don't worry. It's because I have written it, so it's very easy for me to see that there is a bug. Here we have a string, which is a temporary object, and then we take a pointer on the internal content of that string, and then we try to print it. But the problem is that this string was a temporary object and got deleted, and then we still have a pointer on the internal content of it. So in 3 lines, it was already broken. And of course, if you step through with the debugger, you will find it probably quite easily. Now let's take exactly the same issue, but usually it happens more like that. You have different classes talking with each other. Here there is a temporary object somewhere, and we access the internal content of that object, and then that object, we don't really know what happens with it because it's not really specified as part of the interface. And well, later we want to access the content that has been deleted, and it may crash, or it may work actually, you never know. So that's basically exactly the same thing happening, and then it's just split across different classes, and think that it might not be the only classes that you have in that code. There might be a lot of other code around that you have to read as well. And that's why bugs happen actually. And some of them are very easy to fix, so you just master your tools and you will find one way or the other to fix it. And sometimes that's just not working, even your tool is giving up. Visual Studio may crash on the bug, so you have a bug inside of the debugger. Things might get really wrong, and you will need some new IDs in order to fix that problem. But well, this is probably a lot of you are students, as I understand. So if you have only done school projects right now, well, there's something. When I started in a company, basically, I didn't know that, so maybe you don't know that either. I arrived in a code base of 1 million lines of code. I left a school project of like 10 files, if actually 10 files. And you need to find your way in 1 million lines of code and find probably a bug, because that's usually how people start in a company, just to get to know the code. And well, when I started and I had a bug to fix in that code base, I was like, okay. I sat for a day and I thought, what do I do? It's the only question in my head. What do I do? Well, let's see, what do we do? What do we do? Well, this is the general algorithm, and there's also a picture of Dr. House in here. There's a reason for that. This is also the general algorithm in a House episode. You start from the symptoms, you see what's happening, why is it wrong, what's happening that actually is not working properly. You try to understand why, you keep asking why until you know what starts the problem, and maybe there's another reason for that source of problem, so you need to apply it recursively until you find the real reason why it starts crashing, and then you can get your reward, which is not a pay raise, unfortunately. This is really what happens in a House episode, or the inspiration for Dr. House is also Sherlock Holmes. This is basically the same. The difference between normal programming, regular writing code, and debugging is that in debugging you have to think backwards. You have to deduce the cause instead of deducing the consequence. So that's what you should not do. That's very important to me. You don't stop when it looks correct. You need to understand exactly what's happening, and then you need to fix the cause of the problem, not just fix the symptom. Um, this is very important, and it happens more often than we think. You know, you have a code that crashes with a access violation on a null pointer. It's very common. Well, if the pointer is not null, then do the operation, fixed. But of course it doesn't crash, but you don't really know why the pointer was not valid. You just go around the problem. And you don't know what the new bug will be, because probably it was not correct that the pointer was null. So you just hide the bug instead of fixing it. So that's very important. And some bugs are a bit complicated to fix, of course. So the previous algorithm, just start from the symptom and then ask yourself why until you know what's happening. Well, sometimes it looks like it doesn't really help in fixing very complicated problem, either because the symptoms are hard to find or the causes, when you ask yourself why, you really don't know why it breaks, or then you know exactly what happens, but when it comes to fixing it, well, that's quite difficult. So this is when you need to be creative, but actually you will still always do the same things. You will always start from the symptom and then ask why and then fix the cause of the issue. So that thing doesn't change. So if you start from the symptoms, um, you might need to be creative to actually find the symptoms or make them more obvious in a way. Every part of the information can be important, and every part of the information can lie. It's quite difficult, for instance, on network games. You play over the network and someone tells you, I was doing this, I jumped in a vehicle, then I shot, and then I went out of the vehicle, and then I run for 30 meters, and then it crashed. And you think that's very good information, but actually what happens is that another player somewhere on the map entered a helicopter and crashed the helicopter, and the helicopter crashing was sent over the network to the other person and made the game crash on another machine. So actually the information that you got was completely misleading. You need to actually think, is it really what has happened, or did it come from something else? Um, so this is an example of getting as much information as possible. It's coming from a famous programming forum. Someone just said that, which is, well, not a lot of information. It's a bit cryptic, and you think that you need more information. That's true. You cannot fix a bug without even seeing the code, of course, but you can already know some little things about that, and you can actually know quite precisely what has probably happened. You cannot be sure, but you can have a lot of guesses that will prove to be right. So if we start with that error message, um, access violation, so you access memory that is not there at all. So the pointer was invalid. The code was executing this address, but it also tried to read it at the same time. So what happens is that actually the code that failed was not actually trying to read that memory, it was trying to jump at that memory. It thought that there was code at here. And in that case, how can you end up here? How can you end up in that position where you jump to code that does not exist? Well, if it was just static code, the compiler should do a good job and just place pointers that are correct, and it shouldn't send you somewhere on the moon. So it has to be something dynamic that is changed at runtime, and the runtime is incorrect. And the only or the most common way of having dynamic dispatch in C++ is a virtual table, but it's placed in read-only memory, so the virtual table cannot go wrong by itself. But each object points to the virtual table, and that thing could go wrong actually. So if we have a look on a graph, an object has a virtual table pointer, points to the right virtual table, and that's the normal operations. So that looks correct. But actually we ended up somewhere weird. And as we have seen, the vtable being read-only, it's quite difficult to modify the vtable and then jump to that location through the vtable. There's one more piece of information, which is the address itself. If it's not an address, it really doesn't look like an address. It has to be something else. So what we can do is try and guess what this value 3F50624D is. A pretty weird value actually. Well, let's see. If it was an integer, if it was the binary representation of an integer, it would be 1,062,000,000, something like that. That's quite unlikely. We usually don't use that big integers like that. It could be part of a text, part of the content of a string. So it would be divided in bytes, and 3F would be a very weird byte. It's not a character. And then it would be capital P, and then a B, and then a capital M. That's quite unlikely as well. So the last possibility is that it could be a floating point number. And if you convert that binary representation into a floating point number, it will give you 0.814 and nothing after that. It's a number between 0 and 1, quite close to 1. It doesn't have too many digits after the comma, so I don't think that's a coincidence. So actually, we tried to read a pointer. What we got instead was a floating point number. That's most likely what has happened. So somewhere we are accessing maybe an array of floats, or maybe another object with a float at that location. We don't really know. The float value we know, but that's not really helping anymore. We just know that it's a float, and that's good. And what we can guess now is that the vtable pointer has been changed to point at that object, and at the same offset as there was a method, there's now a floating point number. So the virtual table of the object was not correct anymore, but since it's like a hidden field in the object, you cannot really modify it and just say my virtual table, I want it to point somewhere else. So it has been modified by something else, and the most likely cause for that, instead of thinking immediately about a memory overwrite and very complicated things, is that the object was simply deleted and replaced by another object in memory. So what happened from the error message, we can guess with, I would say, I just claim 80% certainty that we just try to call a method on an object that has been deleted. So that's as far as you can go, of course. Maybe you have even more information from that error message, of course, but I think we've already found a lot of things about it. And now we can carry on with digging into the problem and why was that object deleted. If you want to debug properly, you will want the information to be easy to reach, because most programmers are usually very lazy. That's a good trait in programmers, actually. So you don't want to move to someone else's desk and ask them how the bug happened and what happened, and you want them to send it to you, but they're likely lazy as well. So maybe you want the tool to do that for you. You want to build tools that help debugging. You want to create tools that will help you as much as possible, getting all the information that you need without asking for it. You can, for instance, save the crash dumps to the network, and you can even process them and get a lot of information from them without even moving from your seat. You can add a screenshot. It's very handy when you want to describe a bug, an object is rotated, or a triangle is not drawn on the screen for some reason, or you can see through a transparent object. You have to describe it in words, and people don't really want to do that. The best is just to take a screenshot and just show this is wrong. That's extremely easy. You can add more debug text so that you always know where the camera is or where the player is, so you can immediately teleport to that location if you want to reproduce it on your machine. That's quite nice. This is an example of the technology that is right now in the Blue engine in Vanguard Games. Every time there is a crash, the tool automatically uploads the information, complete crash dump on a server. It gets processed, so based on is it an exception or a crash, and it can show nice graphs, but actually these graphs are not extremely useful. They're especially pretty. In terms of functionality, a very interesting uh, thing is that you can actually, from the same web page, from the same server, you can have a look at the call stack when you have a crash dump. You can download the log file, you can download the crash dump to run it on your machine, but you can simply put your mouse on the instance of the crash and just get a call stack with even the parameters in there. So that's extremely handy, and it saves a lot of time. People don't have to report the bugs by themselves. It's all automatic, so they save time, and you don't have to go there and ask for information, at least not immediately. So you save time as well. If you don't have enough information, and that's likely to happen at the beginning, then you need to reproduce the bug. And sometimes it's very hard to reproduce the bug. That's very annoying, and usually that makes people want to stop debugging and just claim that it's very rare and that we don't need to fix it. Well, there are still some tips that can help, and if you really need to debug some code and it doesn't happen often enough, then make it happen often enough first. Don't start by fixing the bug, but start by making it very likely to happen. So you can, there's just a few examples, but the automated tool, we had the problem recently, and I'm gonna talk about it. We just made a tool that just does it for us, and after a few seconds it crashes. If you do it manually, it might take just a few days before you have it on your machine. You can, well, what I mean by making the environment more hostile is to make sure that if it has a chance to crash, it should immediately crash. Some memory allocators are built for that, for instance, so that every time you access a little bit outside of the memory that was reserved, it will immediately crash and you cannot carry on. Otherwise, you might break only slightly, and it's almost invisible, and it happens very rarely, and it's extremely random, and it's extremely annoying to crash. So some memory allocators make it very difficult to just touch memory outside of the correct region. And well, if you cannot reproduce it yourself, you can add some code that will log information, for instance, and then let your coworkers run everything all the time. So you don't increase the probability, but you just increase the population sample. So the example I was talking about, it was the asset reloading. This is a thing that breaks extremely easily. So what happens is you are working with the editor and the game is running, and you are editing a texture. You save the texture. The editor sees that the texture has changed, and it builds the data again, and it sends it to the game. The game reloads the data and displays everything. This happens in less than 1 second, or if it crashes, it happens in 10 minutes. So we want it to happen correctly as possible. But it happens mostly on artist machines. We don't save textures too much as programmers, and whenever we try, it always works for some reason. We have probably better machines, I don't know. So when we want to debug it, that's just extremely annoying. We need to try and save scenes that we cannot create in 3ds Max or whatever program. We have to create textures and edit textures and save them in a program that we're not used to, and most of the time it works for us. That's quite annoying. So we decided to make a tool and ask the artist to create a lot of content for us, and now we just press a button, and the editor is going to automatically try and shuffle some files around and edit some textures and then reload them and build them and send them to the game. And after 6 seconds exactly, when that tool was created, the first time it ran, we got the crash that we were looking for, that we thought didn't exist, and we thought the artists were lying. So they were right, and now we have a very good tool for that. We can run it automatically. Um, Another problem that we run into, which was extremely annoying to fix, is one where the memory gets modified. You don't know by who, you don't know when. It always happens in one kind of specific object, but there are like millions of them, and you don't really know how you're going to tackle that problem. Well, we have decided that it doesn't happen often enough, so we are going to let everybody run the tests for us. So every time there is a play test, people are playing the game, every time people are just working, they are running our debugging tools to check if it happens or not. So we placed memory breakpoints directly inside of the software, and every time it would hit one of these memory breakpoints, it would just crash. We caught it after a couple of days, actually. It was much easier. Without that, without these memory breakpoints, we would never have caught it ourselves, or we would have been very lucky to catch it on our machines. So a few tips that seem very obvious, but people often forget about it. You don't have to fix it on the first try. You can check in some code that breaks even more. It's okay as long as you're not doing it on purpose and as long as it doesn't really make people unable to work. If it happens more often, it's really making your life easier for fixing it. So that's good. You can turn the bug into something else that's something that is a bit unclear. So let me explain. If you have a bug, somebody reports that an object is slightly off by like a few pixels, or if the color of the object is slightly wrong on some of the pixels, nobody can see that except the one who's actually making that object right now. And that sort of visual bug is very hard to catch because people even don't notice it. So most of the time the shaders are to blame, and you have calculations, you have a division by 0 and a few pixels suddenly turn slightly wrong. Well, if you catch such a pixel, if you know that you're going to have such a pixel somewhere, instead of outputting a slightly off color, just turn it red, and then all the objects that have a bug will be red on the screen, and everybody will see what's wrong. You can also find what's the common point between all these objects, and that sort of thing is very helping visually to notice that the bug is here or not. And then you're not working on your own. Some people will know the code better than you. You need to find out who. And if we have different machines at work, some people have machines with more CPU power or more cores. So every time there's a threading issue, for instance, that's likely to happen on somebody's machine who is usually very unlucky, and it never happens on your machine. Well, ask that person to run the debugger, ask that person to help you reproduce it. That's much easier than trying for ages on your own machine. So if you have this information, it's nice, but if you don't have it, if you can't find this information, then you're gonna need to find it somehow to log it. You can add all these possible tools here. Another tool that we have added is a thread checker, for instance. If code is supposed to run only on one thread, but you don't really have any lock to prevent a threading issue, and you don't want to slow down the game, so you don't want to add a lock, we added a tool which is a thread checker. It just checks that it's the correct thread running the code at that point. That catches a few bugs, that logs a little bit of information, and if the thread checker is not reporting any error, you can look somewhere else. It's just information that's now available for you. So you need to think about the kind of problem that you have and what kind of information you want about that issue in order to fix it, in order to use the code correctly. So let's assume from now that you can easily reproduce the bug and you can get more information. We get to the next step, which is why does that break? So you will need to have a way of checking all the possible ways that you end up in that bad situation. Why is this object wrong? Why is there a crash? What's the most likely cause, and investigate what's happening. Uh, and well, you have to look sometimes really everywhere. Just there's always a coworker in your company that was there even before the company moved in. He was probably in the building already, and then they just decided to keep him. He knows everything about the code, and he's going to tell you that code has been there since the beginning, and it has always worked. It cannot be there. Well, it's like denying that there's a bug in the first place, that there is a bug, there is a crash somehow. So if you claim that all the code around you is good, then there is no bug. That's nonsense. So don't believe people who tell you that code is running well. Just think, okay, that's not likely to happen, but that's not impossible. Don't rely too much on your tools. If it's extremely difficult to understand what's happening, the tool might have a problem as well. I remember having some problem with a value that was wrong, but every time I would put a breakpoint in there, the value was changed just before the debugger would hit the breakpoint. So it would look correct in the debugger. But actually it was wrong at the moment that the test was done. It was extremely difficult to debug that sort of problem. But before you blame it on the tool, on the compiler, on the code that was there all the time, just think that the code that was added last week is probably more likely to be bogus than the one that was added 10 years ago. It's very common to, at some point when you run out of ideas, to just say, well, the compiler generated the wrong code. Well, that can happen. I've seen it once in 8 years. It was a new compiler for the Xbox. It was not very well tested. We found one and we sent it, and it was fixed. That happens only once in a career, I guess. The tools are pretty well verified, so just don't blame it first on the tools. Just think that maybe your code was wrong in the first place. So as an example, when I was at DICE, the Unreal Engine kept crashing for like every 2 hours, basically. It was crashing the game, which was Mirror's Edge. And then we noticed that it happens mostly when the character dies and you respawn just a little bit before. So it would happen quite often if you just jump and then respawn, jump, respawn, just respawn, crash. So after a lot of investigation, I started to blame it on uh, their memory allocation and their garbage collector. That was there since 1999, I think, and it was in 2007. So my lead told me, yeah, no, that's not going to be the issue. It's most likely in our code. When talking to my coworkers, they said all the Unreal Engine games that I have, they crash after 2 hours. So it might very well be a bug from 1999, actually. But I looked some more, and after a while, me and my coworker, we were two people working on that bug. We fixed it. It was like a one character change in the source code to fix it. So it was very unlikely, but at some point the least likely possibility is the last one, so it has to be there. When everything, well, nothing is working, you have no information, you have, yeah. Well, it was ready, but we wanted to have for that project something already ready made so that we wouldn't split the development of Frostbite, which was made for Battlefield games. So for another game that was made a bit on the side, that was more creative, we wanted to have just a ready solution for that. As you see, it can always come with a cost. So when you don't have any information and you don't know where to look at all, there are a couple of techniques that you can still use in order to find a little bit more information. It's very difficult in that case, of course. If you have a bug that you don't know what's happening, then you need to start looking in the dark. So you can use what I call shotgun debugging. You just blow away an entire part of the engine and you see if the bug is still there. If it's not, then maybe it was part of that part you just removed. So you can re-add it and carry on until you find a smaller piece that contains the bug. That sort of works, that gives you clues and hints. It may be a good starting point if you really don't know what's happening, but you have to remember that disabling a big part of the code has a lot of side effects. So if you disable physics in the game, well, there's not a lot of gameplay that can happen without physics. So if there was a gameplay problem, of course, disabling the physics is also going to fix it, but you don't really know where it was. Um, we actually use that technique mostly for sound bugs. If you disable the sound, does it still crash? No. Oh, we have a sound bug. That's the one with the least side effects. And another way of looking at a bug without even knowing what it's about is to check if you have automated builds, one of the tools that you could have as well. Look in the history in Perforce or Subversion or Git, whatever you're using. We have a build that is made for every check-in that people do. And so we can test all these builds. We store them for a couple of days. So if you have absolutely no information, you can check all these builds and see when it started happening. If it just started right now, there's a good chance that you can find which change list actually triggered it, and then you already have a lot more information. Unless it was a big integration from another branch, of course, then you don't know. But you can always trace it, and without even knowing what the bug would be, just by saying it happened in change list 1, 2, 3, 4, 5, you can have a look at these files and already spot issues in there. But that's a bit the last resort options. You should always try and find uh, more information. Try to find exactly what's happening. Don't rely too much on luck. And if things get really wrong, then you might be left a bit on your own. You won't have any tool to help you. It happens a lot in release builds. The release build is crashing, the debug build is not. So there's a difference between debug and release, and it just happens that the release bug is the release build is the one without debug information, luckily. So you will have to look without any debug information with all optimizations on, and you will have to find what's happening. You can first check evidently what's the difference between a debug build and a release build. There's code that isn't run anymore because it's removed for optimization. There is the optimization of the compiler, which is added on top. And the debug builds have a few differences in Windows as well. They can use the debug heap, which is more likely to make your memory allocation crash if they're wrong. So there are differences. You will need to start from that. If you have broken call stack, you will need to learn how to walk call stacks from disassembly and from binary or hex. It's not very nice, but if you can't do anywhere else, then you have to do that. And if you don't have the source code, you have to read the assembly code as well. Well, I've used assembly code a bit. I needed to debug such problems where you didn't have any information at all. And I needed to do that for PowerPC assembly and for ARM assembly. At some point, I just forget. Don't learn about that. Don't just there are some articles on the internet about how call stack works. You don't need to study that and learn about it right now. Just remember that if you have a problem that looks like a call stack problem, you will need to find this information somehow, understand it, apply it, and then just forget it because it's just wasted knowledge otherwise. Or write a good article about it as well so that you can teach other people. So basically, don't learn assembly code is one of my tips in there. This is not extremely useful, and you will not use it past the 4 instructions that might crash a game. So just to sum up and be Captain Obvious a bit, this is the general steps that you will always apply when you debug through some code that you don't know or when the problem is difficult. It's always like that. There's no reason to be creative about this part. You always need to reproduce the bug. You always need to gather some information about it. You will always need to add some logging or add some information for the next run. And you will always need to ask yourself, why does it crash? How did I end up there? And then you will need to loop back to the beginning and apply that again on the same problem. So that's the general algorithm, and you don't need to go out of this algorithm. But for each step, you will need to be a bit creative. If the problem is hard to reproduce, you will need to find a good way of reproducing it more. If you don't have enough information, you will need to find a way to log this information or find this information somehow. Uh, and you will probably think at some point, I think I know what it is. And you try it, and it still fails. And that happens a lot. Well, that's still a lot of information in there. Everything that you try, if it works or if it breaks even more, there's some information in there that's pointing at the right direction. And well, unfortunately, if you need to be creative, I cannot tell you exactly how to be creative. That's the point of creativity, unfortunately. So find your own solutions for the kind of problems that you have. For the worst problems, you will need to come up with your own ideas, not my ideas. You will learn a lot by just debugging a bit and by trying to find some information by yourself. So just try and think of a new thing that you might actually want to have, a new information that you might want to have. If your workflow is not good enough, if you think that it's too difficult to reproduce, if you think that you don't get enough information, instead of just using that information, that little information that you have, work on the workflow itself. Work on making the bug even worse until you have enough information. So, have any questions? Yeah. It was the Unreal Engine bug, I think, that I presented here. Random memory crash in their garbage collector. It took me a month and 2 weeks to my coworkers to fix it. And I think the Unreal team should have paid for my salary for that time, but unfortunately they didn't. It was my only contribution to the game, actually, to Mirror's Edge, but I got a credit, my name in the credit for that. I should have probably DICE should have their name in the credit for every game from now on. Other bugs were quite quick to fix, but it took a long time to reproduce it, probably to get when the stars are not aligned, the bug just happens on somebody's machine and it disappears. And then at some point, it just appears at a very good point where you have a debugger ready and everything's happening, and then you can actually find more information at that point. So that was just lucky. Oh, okay. Uh, well, I tested it actually. If you just test that code, most likely it's going to work actually, because even if you delete that object, the pointer, the memory is deallocated, but it's not overwritten. In order to make it break, I had to allocate another string after it would be overwritten. The reason is that you're not storing the string itself. You're not storing it. It's really a temporary object. If you have an object or a reference, then GCC will make sure that the object lives. Yeah. So you need to point at this variable, at the std string itself. Otherwise, it's temporary. The destructor is called. You can put a breakpoint in the destructor to verify. It's called just after this line is executed. Yes. Yeah. We're very drastic with the pointers. We never use row pointers when we can avoid it. The problem is that a row pointer doesn't have any semantic. You don't know what it is. You don't know who owns it and what will happen to it, and you don't know when it's going to die. So when you get a row pointer, it's like danger immediately. Uh, we use, there are lots of possibilities. We use scope pointer as much as possible so that we don't have any leaks. We use weak pointers, but the weak pointers are a bit special. They just, it's like a ref counting, but it doesn't prevent the object from being deleted. It's just that if you have this ref count is more than 0, someone else is referencing that object when it's being deleted. So we got an assertion for that. It means that someone is still pointing at that object. If we had a weak pointer on the text, when the string is deleted, it would tell, oh, I have someone, yeah, I have someone pointing at me. You don't know who, but you know, oh, there's something wrong. That's the, it's explicit using the template and smart pointers, but our own smart pointers. And we have memory allocation debugger, I think, that just tries to place objects within blocks, patterns of memory, and then checks the pattern. Yeah, like most people do. Yeah, most video game companies I've been in, they have their own memory allocator. You can do nice things with your own memory allocator. What is also nice is to be able to place one allocation into read-only memory. You can do that on the PlayStation, for instance. You can just create the object, and when it's ready, you just place it read-only. So the next time someone wants to change it, it will crash. That sort of tool is not available with a normal memory allocator. Mm. Yeah, that's right. No, we do. No, we do memory allocation. The pools that you describe are nice, but they have like space for 10 bullets and 2 rockets. And if there are only 2 bullets and you want a third rocket, then you want to use the bullet memory, basically. It's very difficult to balance everything. So if you have too many pools, then you lose a lot of memory because they are never full. The worst case scenario tells you that you need to reserve a lot of them. That's why we don't do it. No? More questions? 2 more minutes. Well, then I'm gonna. Oh, I need to jump to the end. Do I really want to? Well, there's an ad for our website, and you can find some. We have some open positions for interns and full term. Uh, and so, yeah, there. So just have a look at the website, and if you want, come and visit me. I can tell you more about the company.